Hello! So the purpose of this training is to take a look at these slides here about SingleStore features and to actually show how some of this looks on the database itself. So let's go through some of these slides. This first section is talking about distributed cluster architecture, talking about how it shares nothing. We can actually go and take a look at that. So let's pull up on our host here. So I've already SSH'd up to it, so let me show you how the distributed architecture is separate. This is the one with the master aggregator and a leaf, and we can see that there are two processes running. It actually looks like there's many more processes because each of the services has a couple of processes. But if you look in the actual output here, for example, here we're looking at the defaults file, which is the memsql.cnf, the config file. You can see that the path to that file includes the name of the type of node. Ops does this when it creates clusters, and Cirrus automatically uses ops. So here, this is a process for the master aggregator, so is this one and this one. But if you look up here, this one is a leaf, so is this one and this one. And it's pretty normal to see 2 or 3 processes for each of the nodes. One is going to be the one that starts it up with the service, and then you'll have a watcher that forks itself as a worker. And you can see that with the process IDs over here, which one is which. So if you were going to kill this, you would kill the parent process of all of those. Same thing with a leaf, you've got a service and then you've got 2 others, and again you can see that one's the parent and these are the 2 children. If you do have a cluster spun up with toolbox, you won't have this same directory structure. It doesn't have the name of the role in the directory itself, so you might see something different, but you'll still be able to see the processes. By the way, sometimes you will see more processes. When we are compiling a query, you'll see that as a separate process because it's safer to run that way in case there's anything wrong with the compilation. Additionally, if they have any pipelines, a lot of the time the extraction will be a separate process. You'll be able to see that there. But not only does it run a separate process, you'll notice that those directory structures are different. Let's go in and check that out. This is a custom directory location, by the way. The default for ops is varlib memsql, but we have set it to use EBS as the main data directory, just the main directory overall. So if we go into here, we can see those 2 separate directories. And if you go into, say, the master aggregator, you can see all of its types of files. And in particular, you can tell that these 2 nodes don't share anything because they each have their own separate service file. They've also got their own binary. If you go into the data, you can see that they'll all have their own data as well. I'll go into this more later, but the snapshots and the logs is where your snapshots and transaction logs are. Blobs holds your column store blobs, and all of these are separate for each node. If we go back to the leaf, again, you can see the same thing. It's got its own service, its own CNF file, everything is separate. So going back to that slide, we have a shared nothing architecture. I showed you that the disk is separate, but also we have separate memory, we have separate CPU because it's a separate process. Nothing is shared. Actually, I can show you how memory is not shared between them. I'll just go back to home, and I'm going to use memsql. If I don't provide any options, it's just going to connect. But this is using the defaults of the default port, the default user, and it's connecting with no password since I'm on the host itself. That is permitted. So same thing, I'm on the master aggregator again. So to show that it uses separate memory, we can go and check out the memory allocators. So show status extended is how you'll usually check the memory allocators for a node. And it gives out this big dump about a bunch of different things, but also about a lot of the memory allocators. So let's scroll up to the top. They're not really alphabetized, they're kind of grouped into particular groups. Here's the top. So you can see it's the variable name and the value. And for example, take a look, I'm looking for total server memory. It's actually towards the top. I think I missed it. Sorry, I could also just grep this instead of taking, there we are, total server memory. So the master aggregator is using nearly 400 megabytes. Now let's exit out of here and we'll connect to the leaf instead. The leaf is totally the same except it's on a different port. Let's run the same command. It'll pull the same MySQL history because I'm using the same client. And if we run the same command, and we do have some overlap here, that's why it might look a little strange. Go back up towards the top. Malloc license. Oh, I just missed it. Total server memory. So the leaf is using about 2 gigs instead of the 400 megs that the master aggregator is using. And that's expected because I'm not running any workload on these right now. Typically the aggregators run queries whereas the leaves are storing the data. So this one is storing more data in memory. And that's why its memory usage is different. But so here you can see that the memory usage of both of the nodes is completely different from each other because they don't overlap on anything. And if you look into individual allocators, you would be able to see that as well. That is not to say though, if they happen to try to access the same file, the host memory cache might be able to cache that and use them, but since they all have their own directory structure and their own files, they won't be trying to access the same files. So let's take another look. This is that distributed architecture like I just talked about. Aggregators run the queries, leaves run the data. And next we can take a look at some table types. And when you create a cluster on Cirrus, you have the option to create a demo database at that time. And I went ahead and selected that option. So if we check out what databases we have, you can see that there's all the internal ones as well as MemSQL demo. So if we check out what tables it has, you can see that this is an example of a typical like sales type database tracking orders and parts and things like that. So let's check out what types of tables we have. If you just do show tables, I got this output above, but if you get an extended output, you can see more information. So each of these is a base table, it's not a view. You can see whether it's distributed. This one is not distributed, which means it's a reference table. And you can see the storage type. All of these are rowstore tables. Let's confirm that. How can you check what types of tables these are? You can check out the create statement. Let's do the top one. And this is the command that you would use. It's really wide, but we've got the table and the other column is the create table statement itself. So this is the command that you would use to create this table. You could literally just copy paste this. You notice it's got the columns up at the top and down below it's got the keys. And then outside of the actual statement itself, we have some information that's very specific to SingleStore, and it talks about the auto stats and whether they can be created by default. And this is the default settings for our rowstore table. By the way, I know that this is a rowstore table because we don't see a key, we don't see the column store sort key. We only have a primary key, which rowstore tables are the only ones that can have a primary key. Column store tables cannot. We also have a secondary key. That's another thing that a rowstore table can have that column store tables cannot. For a column store table, it would have to be a hash key if it were a secondary key. And so because it's a rowstore table, the default type for cardinality stats is periodic, and we will create histograms by default. And oh, I would expect to see sampling here. I may have made this on an older Cirrus cluster. Anyway, we also have the SQL mode indicated here. Okay, well let's check out that other table. There was one that was not distributed, so let's see how this is different. So this table is named System, and here's its statement. It's still got a primary key, but note this key difference, create reference table system. So this is how you would create a reference table, is you just have to add that word. By default, it's created as a rowstore table, so that's the actual storage type. It's going to be stored in memory. And as a reference table, it is not distributed. It's not split up into parts and then sent across the cluster. It's sent in its entirety. And so it's created as a rowstore table, and it also has stats. And we'll take a look in a minute here how this looks on the leaves as opposed to on the master aggregator here. But there's also one third type of table that's not created automatically in the MemSQL demo, and that is column store tables. So let's create one of those right now. So we'll just call it this. And I'll show you how I often create test tables. I believe in version 7 the default table type will be column store, and you won't have to use this very long phrase to create one, but otherwise this is how you create a column store table, is you set it to have a column store sort key. And just like the name indicates, that is a clustered index, which means that it's actually stored in the order of this key. And we'll also create a shard key. This determines how we're going to be splitting up that data into the partitions. All right, so it's created. So now if we check out extended, you can see that the storage type is column store, and it is distributed, which is the default for column store. I didn't say it was a reference table, and it's distributed again on the shard key A. And we can see that. So we've got some overlap here, but you can see, oh, this is why it wasn't showing before. So you can see here it says sampling is on, and that's the default for column store tables. For row store tables, you can't disable it, so that makes sense why it wouldn't show what its value is, because it has to be on for row store tables. Okay, so we've got our table here. By the way, another way that you can see this is by using the command describe. You'll get a different format, so you can see the fields and then the details about each of those. But as you can see, it can be a little misleading because this is more like a MySQL format. So it's calling A the primary key, but as we know, A is actually the clustered column store key, which is not a primary key. So that is a little bit different, and we can see there's no keys on column B. And that's because a lot of SingleStore keys don't actually agree with MySQL keys, so you'll get weird results here. All right, so we've got this table. I talked a little bit about different keys, and you can take a look at those, but the main thing to remember is row store keys can have many secondary keys, whereas for column store, if it's a secondary key, it has to be a hash key. We're also adding support for more types of unique keys on column store, and reference can just take whatever key according to the table type it is. This next slide here is talking about how we store the reference table. So let's go and check that out. So on the master aggregator here, you can see that that reference table system is just here. Oh, let's also insert some values before we move on to that. Let's insert some values into test column store. Oh, I set it as a shard key, so I won't be able to do that. Instead, I would do a test creation table. Yeah. There's a bug on the way that we do rand if you set that column as the shard key. In fact, I'll go ahead and do that so you can see what this looks like. And it will object, saying you can't use rand to insert into a shard key column in a distributed SingleStore. And the reason for this is there's a bug in the way that we call this. We call rand once for determining which partition it would be distributed to, and then we call it a second time for actually generating the value that is put into that partition. So you would actually get a different value and it would be sharded to the wrong location. This only occurs when people are generating random test data. So the way that we have handled that is that we don't allow to use random to insert into a shard key column. So instead, what you can do is create a filler table that has no shard key and then use that. So I'll insert one value, and then I'll do an insert select to double it every single time. And you can see it's going up exponentially. I'll be using this to fill up a column store table. So let's go ahead and get, well, I'll call this good. Okay, so now we'll insert these instead into my column store table. And instead of doing random, since it will be complaining about that, I will just select all. And then one other thing I'm going to do here that I didn't do for my filler table itself is that I want these values to be uniformly distributed across all partitions. And actually I have a shard key in this table, so it won't matter. But if you want your values to actually be redistributed evenly, you will need to use a hint when you're doing an insert select. Otherwise, they just get inserted into the same partitions from which they originate. And the hint that you'll use is I think that's it. We'll find out. No, it's not it. Oh, I think it's reshuffle. Those are two words for the same thing. That one's it. So it doesn't matter because this table actually had a shard key, but if your destination table does not have a shard key, then you want to use this to make sure that those values are redistributed. Because let's check out where our values are for those two tables. And this is a trick. This is a function that actually tells you what partition ID the values are coming from. So I like to use that when I'm checking out how many values are in a partition. And I'll group on the second column, which is that partition ID. So you can see only in partition number 4 we have all of those values. However, if we check out our other table, we've got it on all of the partitions. And it's about even. This, when it was inserted into filler, well, I guess it doesn't matter, but when it's inserted, it'll do it as a round robin. If there's no shard key, it'll do it with a random function that tries to be roughly even. And then when it insert selected into test column store, it did it as per the value of A, because that was the shard key that we chose. Okay, so we've got lots of data in our column store table now, and we can see that it's distributed across all of our partitions. Let's actually make this a little easier to see. We'll order by that partition ID as well, so you can see we have 8 partitions and we all have data. Cool. How about that reference table? What does it have? Well, it has 4 values, and the partition ID is null. So why is it giving us that? Let's pull out some of these things so we can see the actual underlying data in that table. Alright, so this table system only has, for itself, it only has two values, name and data, and we added the partition ID. But for each of these, there's only 4 rows in the table total, and none of them has a partition. The reason for that is because it's a reference table, it's not partitioned. So let's look into that a little bit further. This again was on the master aggregator. The reference table is stored on the master aggregator, and that's where we can write it. It's the only place where we can't. What about if we are on the leaf? Well, right away you'll notice something interesting. We have more than one database named like MySQL Demo. On the leaf, you can actually access all of those partitions. This is partition 0, partition 1, partition 2. We do actually have all 8 partitions on this leaf because I only have 2 leaves in the cluster and I have high availability, which replicated some of the partitions. So this is something that I would never recommend to do to a customer, but we are going to go in and actually query the data in the partition databases. On the leaf, it actually uses the same binary as any of the aggregators, and so what it's doing here is treating each of these as its real own database. So if you were going to use one of those, you can see that it's got all the same tables. Well, what happens if we want to check how many values are in customer here? Actually, let's use the one that we were looking at the values of before. Well, we've only got 76,000 values here in our database, demo 0. If we look up here before, in partition 0 for this table, indeed, we had 73,000 values. So that's what you can see here is on the partition database, you can really only see just the values in that partition. And this is why we recommend that customers never try to manipulate data directly on the leaves, is because you only see part of the data, only the data on that partition. All right, so what about this one? What's that? I don't think you can even do this. Here, let me do it. Okay, so you can see the tables again. So this on a leaf, this is the reference database, and the reference table itself is actually stored in the reference database. So you notice here on the leaf in the reference database, we've got all 4 of those. I believe, so I'm using the partition database again. Yeah, so here actually it doesn't exist. You'll see there's no table called system, and that's because system is actually stored in the reference database. Other things stored in the reference database are things like metadata, but the values for this table are actually only stored in that reference database. So again, if you see that, for example, if you check out show cluster status or any other commands on the master aggregator where you see a database structured like this, this is going to be the partition database, whereas this on a leaf is going to be the reference database, and the reference table is stored in there. So that's how we replicate a copy of the reference table out to all of the nodes, is we get it as part of the reference database. Cool, so they're not partitioned, they're spread out to all of the nodes, including to the child aggregator. I can show you that too. Let's SSH to that host that has the child aggregator. And I'll connect up to it. This is the aggregator because it's on port 3306. I didn't show you that. So we would be here on this one. And if we check out the databases, the child aggregator does not store any data. So it doesn't have any of the partition databases, but it does have a copy of the reference database because it needs to know all of that metadata, just like the aggregator for constructing distributed queries to send out to the rest of the cluster. And it also has a copy of the reference table because it has the reference database. So you can see all of these tables, and again, this is just metadata about those. And if we use this one, we can see those values for the reference table in the reference database on the child aggregator. Pretty cool, huh? One thing to note is that when this table is written, we can't write it here on the child aggregator. I'll just copy something we already have. I don't think it has a primary key on any of these. It will say, hey, you can't write it here. And the same thing will happen if we try to do it on a leaf as well. Which one am I using? I'll just say. So I'm using the reference insert. And the leaf gives the same reference. You can't modify a reference table unless you're on the master aggregator. So if we go back to the master, we can actually do that. We have to say. It actually does have a primary key. Okay, so it has a primary key on name. Alright, so here we can see that value that I inserted. And if we do the same thing here, that has replicated out to the child aggregator already. Pretty cool. Alright, what else do we talk about? Oh, we talk about partitioning. So yeah, let's cover that and then I'll let you go. So partitioning in rowstore tables is horizontal partitioning, which means that we keep the rows together. So based on the value of the shard key, we take all of the rows that have the same value of the shard key and we put them into the same partition together. So let's go check that out. Let's go on the master aggregator, because again, if we want to query our data, we need to do it on the master aggregator. I mean, I guess what we're doing is kind of broken, so we could do it on a leaf, but we'll do it here. Alright, so let's do it for a rowstore table first. I'll just pick the top one again. What do we want? What's the shard key of this table? So, what is the shard key of this table? I don't have any shard keys. These are my columns, they come first. These are my keys, they come after that. Well, on a rowstore table, if you don't have a shard key, the primary key is used as the shard key. So let's go and grab some values for just one of those partitions. I wonder if this will be very obvious, because customer key is, I just happen to know this, it's like an auto increment. It isn't actually an auto increment, but I know that all of its values are unique. So it might not be very easy to see that. Let's actually make our own table. Yeah, and I only want just the shard key. Okay. And again, remember we need that hint. Just fix my spacing. Fix my typo. I bet you were just sitting there going, oh, fix that typo. Oh, actually I didn't want the values in it yet. So I want to show you when we insert those values what it looks like. I did set a shard key, so I have to populate it manually. Oh, that is a pain. Alright, so I've inserted the same value 4 times. So do you expect that those will all be in the same partition? I do. So yep, all of these are in partition 4. Oh, you can't do that. So if I wanted to see all of those values, I can just filter on that partition ID. And I have to actually run the function in the filter as well, because you can't refer to column index in a where the same way that you can in a group by or order by, the way that I did earlier. So let's filter. Cool. So these are all of the values that are in partition 4. What about if we insert some other values? So I want a different value of A. Let's keep the value of B the same. All right. I'll do 3 of those. So first, let's check what partition they're in. I made 3 of them and they ended up in partition 3. So you can see that those are all in the same place. What if I can't randomize it, I have to do it manually. Okay. Let's figure out where all of these go. No, I'm not going to make this more exciting too. Very exciting. I hope that you speed through this section. So I've inserted 10 values, but if you remember, how many partitions do we have? 8, right? Actually, I've inserted 11 values because it's 0 indexed. Oh my gosh. Okay. So where do these values end up? Well, in partition 0, we actually got where A is 0. In partition 1, we got where A is 5 or 7. That's because of our bucketing. We only have 8 partitions, so we're going to end up wrapping around and putting some values in the same partition. What about partition 2? That only gets the 8s. 3 got 2, 4, and 10. And again, this is just going to depend on what hash index is ended up being used to shard those keys out, or excuse me, hash function is used on this column to determine where which bucket it ends up in. Because bucket 4 ends up getting 1, 3, and 6. Bucket 5 got 9. So we're going to try to choose a hash function which is going to roughly evenly distribute them, but we didn't get any values in buckets 6 and 7. So that'll just depend on what values you're inserting and what hash function is being picked internally and used in sharding out to them. But the important thing is you can see that, for example, all the values of 10 are in the same partition. They're in number 3, regardless of the values of B that I inserted, because only A is in my shard key. You can actually set a shard key on multiple columns, and then if we had different values of B, then, for example, say that my shard key was A, B, then I would first be ordering by A, which is 10, and then ordered by B, which is over here, 7 and 6. So all of the values where 10 and 7 were the same would be in the same partition, and all of the values of 10 and 6 would be in the same, a different partition probably. And so adding another column to your shard key gives the database a way to break up large blocks of values. So that I had 1,000 values that were all 10. I could break those up by adding another column so that they can be in different partitions. And that's one way to effectively resolve data skew. Say that I had only 8 partitions and I had only 5 unique values, but I had maybe 1,000,000 rows inserted. Well, I would only get values inserted into 5 of those partitions because I only have 5 unique values. So to get values into the other partitions, you could add another column to your shard key so that it gets broken up into smaller pieces and distributed across all of the partitions. Cool. So that's one way to resolve data skew. Add another column to your shard key. And what happens for column store tables? We do the same thing for the first step. We're going to horizontally partition. So the rows stay together in the same partition on the same host. But once they get there, they're going to be broken up into column store segments. Those are also called blobs. That's not going to look any different when you query it because they get put back together. But you can, I guess you can't really see it even. But the way that the files are stored, you're going to be storing each of the segments separately is a separate column. So to go back to our example, column A, if this were a column store table, column A would be stored separately from column B, even though they're stored in the same host, in the same partition. They're just separate files. Cool. Well, that is the end of that section. The next recording I will do is about storage. So again, this was Distributed Cluster Architecture, and I hope you enjoyed it.